Let's talk about our last topic for the chapter, which is on catalysis. So many common reactions need high temperatures to proceed quickly enough, like burning gasoline in cars. When we want to go fast, we don't want to wait for the temperature to rise and get the molecules excited and all that. We want to go now. All right. What about extracting metals from metal ores? Again, we want this to be very quick, very quickly. This phrase time is money. Well, you got a lot of people trying to extract metals from metal ores, and it takes a lot of time. So we need a process to make this go faster. What about cooking food? Sometimes when we're in a hurry, if a recipe, let's say we're baking a cake and the cake is supposed to be baking at 350 degrees for 20 minutes, well, if we're in a hurry, sometimes we got to raise the temperature, and hopefully that lowers the cooking time a little bit. Okay, although I will say that sometimes playing that game can make things, that can be a real dicey scenario. There's other reactions. There's other things in life that sometimes it takes a lot of time to do something, and sometimes we just need, we need help to make things go a little bit faster. Now, for reactions in the body, this is it's not practical to have reactions occur at higher temperatures because at higher temperatures we die. All right, so it would hurt if it got that hot. So what does the body and what do other living systems do to permit fast reactions at modest temperatures like our body? Well, we have a class of biochemical compounds called enzymes that help us out. Now, usually when we look at a biochemical compound, a dead giveaway that it's an enzyme is its ending. Its ending has the suffix ase, and usually that indicates that we're dealing with an enzyme. Okay, so we're dealing with a compound that's supposed to speed up a chemical reaction. So, for instance, we're looking at the name of the compound that's used by legumes to use N2. And so that compound that helps legumes use nitrogen is nitrogenase. Okay. And what does using nitrogen require such a compound? So think of it this way. Nitrogen, N2, its Lewis structure looks like this. So you've got a triple bond between those two nitrogen atoms. So its elemental form is extremely stable because of that triple bond. Okay, so let me write that down. The elemental form is extremely stable. Now, another way that we can talk about stability is using the bond dissociation enthalpies. So remember, we had talked about this near the end of Gen Chem 1. If we were to look up the bond dissociation enthalpy for N2, that would be about 945 kilojoules per mole, which is a lot of energy. So it's going to take a lot of energy to break that triple bond, which, a plant does not have 945 kilojoules just sitting around. So, how much faster can a reaction proceed with enzymes? Well, sometimes it all depends on the reaction, all depends on the catalyst, but sometimes we can see a reaction move as quickly as 10 to the sixth times faster. Okay, so enzymes can definitely speed up a chemical reaction. Now, so these are the things that we use for living systems. More general name for these substances are called catalysts. Okay, so the text does. Where I grabbed this from, there is an example of hydrogen peroxide decomposing with the addition of iodide ion. So if we were to look at that mechanism, it's actually a two-step process. So let's take a look at this. So in the first step, you got H2O2. And then we're adding iodide ion plus I minus AQ yields water, H2O, and then IO minus. Okay, so that's the first step. And then we take the water that was generated in that first step. Okay. In this case, I'm sorry, I goofed. Instead of taking water, it's going to be another molecule of peroxide, H2O2. And then we react with IO minus from this first step. Okay. And that gives us another molecule of water plus I minus. And then we also release O2 at the same time. And that should be a gas, not aqueous. All right, so there is something really going on. Look at iodide. Iodide is a product in the first reaction, and then, or in the first elementary step. In the second step, it's also a product. And so this actually shows us, this actually tells us something really, really, really important about reactions that use catalysts. If you put a catalyst in at the beginning of a chemical reaction, you need to be able to get that catalyst out at the end of the reaction. So that's actually something really nice about this mechanism. It shows that really quickly. All right, you put the iodide in, you get it out. All right. So in the first step, this is going to be our slow step. This is our rate determining step because we need IO minus, which IO minus is turned around and used as a reactant in the second step. So everything's hinging on the production of IO minus. Okay. So if we were to look at the overall reaction, okay, and I know I'm missing some, I got to fill in some stuff here, but I will in a minute. If we were to write the overall reaction and cross out the things that show up on the left and the right hand side, so I minus we know is a catalyst because it shows up on the left and the right. So on the first step we used it as a reactant. Last step it's now a product because we're trying to spit it out. Okay. IO minus also shows up on as a product in the first step and then a reactant in the second step, so that's our intermediate. Okay. So that being said, if the overall reaction would be 2 moles of hydrogen peroxide yields 2 moles of H2O plus 1 mole of O2. So that would be the overall reaction for this mechanism. Okay, so let's go back and answer some questions now. What is the role of the iodide ion? Well, we know it's a catalyst. Okay, and how do we know that? It was a reactant in step 1, and then a product in step 2. Okay, is iodide ion in the rate law? Ooh, so this is a good question. Is it in the rate law? And the answer is yes. So remember, if in order to write a rate law, we can write a rate law based on the individual steps. So if we know that the first step is the rate determining step because we need IO minus, we need to produce that. The rate law for step 1 would be that the rate would be equal to the rate constant K times the concentration of peroxide times the concentration of I minus. So that would be the rate law for the first step. Okay. Why is it of this form? Because the first step is the slowest step, or rate determining. Ooh, I went backwards. Sorry about that. So that was the rate determining step. Okay. All right. And I just realized that should be why is it of this form? The rate law should go right there. Okay. So now here's our thing. Here's our next part. Draw potential energy figures for the standard decomposition and the iodide-induced one. All right. So what we should see is that if we were to allow hydrogen peroxide to break down on its own without the iodide, it would be a one-step process. So here what I'm going to do, on the y-axis, I'm going to put the change in energy. On the x-axis, this is going to be the time. So what I just did was make the straight line. This is going to be the energy of the product, reactants, and then here are the energy of the products. Okay, and so for this reaction, and I'm going to do this in green, the graph would look something like this. It would go up to the point where you hit a plateau, and then it would proceed. Okay, now the energy, the activation energy for that reaction, if I was to find the energy level of the reactants and the energy level of the products, okay, the difference between the two energy levels, okay, the energy level of the products versus the energy level of the reactants, we know that this is the change in energy for the reaction. Okay, and if we were to measure the energy level from the reactants all the way to our maximum point, that difference right there is going to be your activation energy, which for this reaction is a value of 76 kilojoules per mole. All right. So it's a one-step process to break down hydrogen peroxide over time. What if we had the same reaction, but this time we put in that catalyst? Well, according to what we had before, it was a two-step process. So how would that look on this kind of a diagram? Okay, so let me draw that in. So what I'm also going to do is make sure that the energy levels are matching. So here's your energy level of the reactants, and then here's the energy level of your products. Okay, so this time what I'm going to do is draw in our graph. Now keep in mind that this is a two-step process. The first hill or the first step is the rate determining one, so that's the one that's going to hold us up. So that's going to have the high, that's going to be where our activation energy for this reaction lies. And then we have that valley, which is where our intermediate forms, and then we're allowed to proceed. Okay, so here, so just like we did for the previous one, if I find the energy level of the products and the energy level of the reactants, the difference between the two should be the change in energy of the reaction. Okay, and it should, in theory, these two should be very close to each other. Okay, now the only difference is the activation energy, because we added in that catalyst, that activation energy should be lowered. So instead of being 76 kilojoules per mole, it's now 57, just because we added that iodide on. Okay, so what is the percent decrease between these values? Well, if you take 57 and divide by 76, it should be a value of about, it should be a quarter, so it should be 25%. Now, is the change in rate greater or less than this? Okay, so is the change in rate greater or less than 25%? And it's actually greater. And the reason for that, it's the exponential nature of energy distribution. Okay. Now, there are numerous types of catalysts, and so they can be characterized in many ways. So you could have a natural catalyst versus a synthetic or man-made one. You could have a biological catalyst versus an inorganic one. Now, one important distinction among the catalysts is the ones that occur in the same phase as reactants being in a different phase. So if it's in the same phase, we say that these catalysts are homogeneous. And if they're in different phases, we say that these catalysts are heterogeneous. Okay. Now, each type have its advantages and disadvantages. So the same phase advantage means you're going to have good mixing. Same phase disadvantage means it's going to be hard to remove for reuse. Okay. Different phase advantage, it's going to be way easier to remove, to reuse. Okay. Different phase advantage, what that means is that it's going to have limited contact between the catalyst and the reactant. Okay. And so this figure, which I stole from another textbook, is actually a really good example of a different type of phase catalyst. So in this case, you're trying to bring hydrogen and you're trying to bring ethylene together. Okay. Both molecules are incredibly stable. So the way that you want to bring them together, so that way you can form a bigger molecule to form ethane, is to have them be absorbed or basically held onto the surface of a metal. You break the hydrogen bond, the bond between the two hydrogen atoms, and then one of those hydrogen atoms is going to be transferred to the ethylene molecule. And so once that ethylene molecule picks up that extra hydrogen, we're able to break that double bond, and then that extra hydrogen can be added on, so that way you form ethane. Okay. Now, many of us use a heterogeneous type of catalyst today in our cars. So we use something called a catalytic converter. And what a catalytic converter does is converts carbon monoxide to CO2, to carbon dioxide, and it also converts NO to N2 and O2. So that way it makes cars just a little bit more safer for the environment.